going to be working out rules of Syn Dihydration. So we covered anti-addition before, and the questions that you ask yourself to determine what the product will be. So in this case, is it an alkene? Yes, so you break that pi bond and you add your alcohol to both sides. And it's going to be the anti-addition if we're using acidic conditions. If it is symmetrical, right, then it is going to be meso. However, if it's a Z or an E product, then it's going to be only one product. Okay, if there's a chiral center, then it's going to be stereospecific. Now we're going to apply these rules. We're going to apply them to Syn addition. Okay, so Syn dihydration using a new set of molecules. So let's look at our reagents and those mechanisms involved in them to just establish our rule page so then we can work out problems. Okay, so here, let's say we have osmium tetroxide. Okay, so here is that molecule. And we're going to ask ourselves, how does this form an ester? How does this add for alkenes? So we're going to have first the double bond is going to break off and go to an oxygen, and then this oxygen, it will break the pi bond, and here we will have then this double bond is going to go to the other side. Okay. So what product will we get from this? Well, we're going to have, remember, we're doing Syn addition, which is going to look like this. And now we want to do our dehydration and produce a diol. So let's add our two groups across the same face in this cyclic osmate ester. So we're going to use aqueous sodium sulfide. As well as H2O. Okay, and we end up with Syn addition of alcohols. So this method, it's used to convert alkenes into diols, our intermediate step. And as a reagent's consumed in the catalyst, it produces a large quantity of your diol. So a co-oxidant is something that is going to help in this reaction to make it more stereospecific. And here we'll use N oxide, which is NMO. So using this catalytic reaction, we're going to show the reversal. So here we have our alkene, and we're going to treat it with our catalyst as well as NMO, and we're going to get a Syn addition of alcohols. But now if we're going to use, let's say we want to use a different hindered base, we're still using our catalyst, but here we're using, let's say, a tertiary butyl hydroxide. So it's got 3 methyl groups attached, and you'll get the same product, roughly 60 to 90%. All right, so although it's the mechanism's similar, the Syn dihydroxylation involves treatment of alkenes with cold potassium permanganate under basic conditions. And so, as we covered earlier, that both will add across the double bond, and there are similar mechanisms. However, potassium permanganate is less expensive and it's a strong oxidizing agent, and it produces a higher percentage of the diol. So it's often chosen as a co-oxidant to achieve Syn dihydroxylation. So now let's compare this mechanism across the board, okay? Here we go. Okay, so I'm looking at how this reaction worked. Okay, I've got that in my side notes, and here I'm going to work on some problems. So the reason I am going to choose these alkenes is because we've already seen them in different reactions. So we can consolidate our steps in a few different ways. Here I'm looking for a general set of rules that I can use as I work through these. So the same set of questions applies where I want to ask myself, do these have chiral centers? Are they symmetrical? And identifying foremost, is it an alkene? All right, so let's go back to our rule set. Is this an alkene? Yes. So we're going to be adding an OH on both sides. And is it anti or syn? So let's go ahead and write it is an alkene. Is it symmetrical? Yes, so I'll just draw a plane of symmetry to show that. Okay, so it's going to form, it's symmetrical. Not on that plane though. So you can say, is this cis or trans, E or Z? And so it's going to be trans. And does it have an area where it can produce chiral centers? Yes, 2 chiral centers. Now here we're focusing on basic conditions. So I'll use blue to signify that. Okay, so in the first one, we're going to use our catalyst and our co-oxidant oxidative NMO. Okay, that nitrogen really helps to remove an additional oxygen, and we know in basic conditions we are going to get what type of addition? Okay, we're going to get Syn addition. Okay, so what does that look like for us? So our initial structure is going to remain the same, and we're just adding across the pi bond two alcohols. And here's our Syn addition. It was only symmetrical on one plane, so you will still have an enantiomer. Okay, here we have our next one. And let's say that we're going to add cold potassium persulfate. And this is the one that you'll see most labs. We'll soak up some of those additional water molecules using a sodium hydroxide, and it's going to be under cold conditions. So usually stir this with ice. And we like using this because when you're treating a alkene with potassium permanganate, it's spelled here, I can never say it. Perm and ganate, permanent, I can't say it. Okay, and you'll end up with one product. Doesn't matter. Remember, it's adding the same way whether or not you use basic or acidic conditions. So stereochemistry is not relevant. Okay. There's our line of symmetry. Here's our next alkene. Is it symmetrical? So it is an alkene. It's not symmetrical. And do we have an E or Z? Okay, so we have two hydrogens on one side, and here we have a methyl and a hydrogen. I'm going to go with this being a Z product, same side, and it's not meso because it's not symmetrical, and we're going to do addition under basic conditions. So let's choose what basic conditions we would like to treat this one with. Let's go ahead and use osmium tetroxide. Let's soak up the extra water it's going to make with some salt. And this is very basic, and we're anticipating water. All right. So back to just looking at this simply. I want to just only look at the molecule for just a little bit of ease. Easier on the eyes. Yeah, so this molecule, we're adding across the pi bond. How many chiral centers can we have? Well, remember, we have our two hydrogens. So this is not chiral, so we only have one chiral center. So we're going to get addition, or okay, adding alcohol here. And on this side, we're adding an alcohol, but it doesn't need to be stereospecific. And we will have an enantiomer. All right, how do we want to treat this one? It doesn't have a plane of symmetry. It only has one potential chiral center on our pi bond. If we're treating it with basic conditions, like let's use this again, our catalyst, get this going, and then something really hindered. So if we're treating this one with this, we're going to end up getting what product? We're adding our oxygen, or alcohol, Syn addition to both sides, but we're going to have this product as well as its enantiomer. Alkenes will be a lot in this upcoming chapter. We'll keep going. We'll keep seeing it. It's going to keep coming back. Here, let's just go ahead and treat this with something we'll see a lot of, the potassium perchlorate. And then we're going to get that extra water, but the reaction won't go too fast because it's cold. Here we have a plane of symmetry in our meso product, so we will get a meso product because we're adding on each side of the pi bond. And it's that simple, right? And there's no enantiomer because, right, it's going to equal the same thing as if we had this. Now, do you remember how to get the same product using acidic conditions? So those are the things that you'll have to memorize for acidic conditions. Here we have a little bit of a reminder. So acidic is going to be our peroxy acid. In aqueous conditions, and what will this produce, right? So this one will produce a meso compound as well. Anybody want to figure out how to draw this? So let's create some space. Okay. Here we have this one, and now we're focused on an acidic workup. So this is where repetition becomes your friend. And what I'm doing right now is I just want to make 100% decision that it's correct. Okay, so if you're adding anti-addition, you actually don't get a meso product. So this was one of those kind of tricky solutions because you're adding Syn addition across a pi bond, and there's going to be all kinds of ways to remember this, right? So this is where it comes in handy to know that this was what type of plane of symmetry? Okay, cis. So you don't end up with the same product when you're adding acidic versus basic on a cis. let's go back to a trans, like this one. Okay, if we were treating this with an acidic workup, okay, here, let's just make the whole thing smaller. What happens now when you treat this product with an acidic workup? You're going to get Anti-Dihydration. So that's going to look like this. So not the same thing. This is one of the few examples, and the reason that this is an example is because it's a Z product, right? Z equals same. And you only have one chiral center. So that's when you're going to end up with a product that will be the same using both acidic workups as well as a basic workup. All right, chapter 8, and then book by Klein, Organic Chemistry. And this is one of those really important things to learn, because as you move on with reactionary or reaction chemistry, you're going to just keep seeing more of these examples where you have to compare whether or not it's a meso product under acidic or basic conditions. So I suggest going through and only working on basic, then only working on acidic, and integration at the end. All right, so here's our rule book, here's our molecules and what we're doing. And on our last question here, now let's solve this for both basic and acidic conditions. Okay, so basic conditions. Which one shall we use? Let's use a catalyst and NMO. Okay, so we automatically know that 1, it is an alkene. 2, it's not symmetrical, so no symmetry. And 3, are there going to be chiral centers? So the answer here is yes, 2 of them. So now we're looking at this. Is it an E or Z product? Nope, because it's chiral on both sides. So we can go ahead and we know that when we're adding basic conditions, and let's just make that a 4th category, basic conditions, it's going to be Syn addition across that pi bond at the chiral centers. All right, so knowing all of that, right, this is what I call just going through the general rules, so that way you can see a problem, solve a problem. Okay, so we're drawing our same molecule. Let's draw it without the double bond. We've identified our chiral centers are going to be there and there, and we've identified its Syn addition. So let's go ahead and add our oxygens. All right, and syn, I want to keep them on the same side. Okay. How does that look? Well, it actually should be flipped. You shouldn't have. So this was one thing that will help keep you organized. You're going to have an H here. So wherever that H is where you're going to draw your new formation. I did it on the top. I need to do it on the bottom. Okay, so OH. And that's going to be our answer. So now if I'm going to use this and let's say under acidic conditions. All right, so what am I going to have if I do this? Okay, so let me start off by drawing my functional groups. Okay. And I've broken that pi bond. First thing first, I know it's an acid, so it's going to be anti-addition. Was there anything special about this? No, it's all the same, right? So you have an alkene. Instead of rewriting it, I'm just going to check. There's still two chiral centers. This is the only difference. So anti-addition is going to look like what? Right? So I'm adding like this. And I can always, hold this one still and rotate this one around. It's going to be the same as plus enantiomer. So that would be the same as writing this. So now we see that these are the same. We can see that this forms a cis, and this forms like a cis addition of oxygen. Well, alcohol across your pi bond. And then this produced and I should have written this in black, a trans. Okay, so now we know if you see this question on an exam, you're going to get either a cis, trans, you're adding alcohol to the pi bonds, and with basic solutions, it's going to be syn. And under acidic conditions, it's going to be anti. Okay, so cis, double alcohols across the pi bond, anti. Okay, and this is what we can just call a logic series. And I'll show you what a logic series is. And I know this is getting a little too deep, but maybe I should step back. right? So if this is my new rule page, because now we've expanded to integration, where we're adding up ideas. Okay, I want to add a new page now, so here we go. Yeah. Okay, back out of this. Here's a new one. Okay, here's my rule book. So this is a rule book for when you're adding anything across what do we know about this one? It has 2 chiral centers. Is it, so let's see, is this E or Z? It's E. They're on the opposite side. I'm just looking at the 2 that are equal, right? 2 methyl groups, opposite side, calling this an E. So we know that you either have a Z or an E. This is an E, so it's going to be an enantiomer. That's a giveaway, right? We'll have enantiomers. And we want to know, let's say, how do you turn this molecule, okay, how are we going to turn this alkene into a this is, wonder why it's frozen. Give it a minute. Well, I'll have to continue this.